In addition to the list of existing functions are exponential functions. An exponential function is of the form y equals b to the x, where b is the base and x is any real number. The number b is considered the base, as I said. However, mathematicians tend to use the general function y equals e to the x. Now, what is e? E is a special type of exponential called the natural exponential function, also known as Euler's number, and it equals 2.718281828. But what is so unique about e to have its own special number? Well, e is a number that shows up in many places, including statistics, finance, engineering, and especially calculus. For this reason, e is given its own characteristics. Hence, the exponential function is a reflection of growth and decay seen in these sectors. The origins of the number e dates back as far as 1683, where Jacob Bernoulli examines continuous compound interest and makes the first approximation of the number e. However, it is Euler in 1748 who publishes his ideas surrounding e, providing an approximation to 18 decimal places. The base of e is used interchangeably with the base of a fixed number. Nonetheless, both satisfy the uses of exponential functions.
As explained earlier, an exponential function is a function whose value is a constant raised to the power of the argument. Let's consider the example of Greg, who takes his $2 bill to the bank and they are telling him that he will get a 50% increase per day. At day 0, his investment is $2. 50%, we must times this by 1.5 and we get $3 after day 1. We went from here to here by timesing by 1.5. Similarly, for day 2, we take the previous amount and again times it by 1.5. If we continue to do this, we will see that we are constantly timesing the previous amount by 1.5. From here to here, we times by 1.5. This pattern is one of the main concepts of the exponential model. I want to draw your attention to what happens between the day 0 and day 1. The change in Greg's money has gone from 2 to 3. This is a change of 1. If we look at the change from day 1 to day 2, it has changed 1.5. Day 2 to day 3, it is 2.25. The change between day 3 and 4 is 3.375. If we take the change in Greg's money over the initial value, for example, 1 over 2, we get 0.5. If we do this for all of them, they will all be 0.5. This is one of the main properties of exponentials. In general, this is the concept that the change in input is proportional to the input, or for Greg's case, the change in dollars is proportional to dollars. Now, Greg's brother Jack walks into the same bank and they offer him the same deal, except his initial value is $2,000. One important thing to note here is that the percentage change for both of these two characters is still going to be 0.5. But since Jack has a higher initial input, he will receive a higher return as the change in the input is proportional to the input. One of the main differences between a linear function and an exponential function is the position of the unknown. As we can see, the unknown x is an exponent. X represents periods of time. Now what are A and B? A is the initial value. In Greg's circumstance with his investment, the initial value was 2. Now you might ask, why is 2 the initial value? Because if x is time, then the initial value of x will be 0. We know that any number to the power of 0 is equal to 1. Therefore, a times b to 0, no matter what b is, it will always be the initial value. Now we know what A represents, let's focus on what the letter B represents. B is known as the growth or decay factor. One important property of B is that it cannot equal 1. This is because any number, any base with an exponent, no matter what x is, whether x is 100, it is still going to equal 1. If B was 1, this function will not be increasing or decreasing, it will simply be a constant. The value of B determines how quickly things are growing or decaying. In Greg's scenario, his investment is increasing at 50% per day. Therefore, his value of B is 1.5. It is important to note that things become a bit tricky when the value of B is less than 0. Let's say the value of B is less than 1. If the time is half, we can rewrite this to the square root of -1, which we know is a math error. Another important aspect of B, in this case the function was growing. If it was declining, the value of B would be between 0 and 1. For instance, if Greg was told that for somehow the bank was rigged and his money was decreasing 50% per day, the value of B would be 0.5. Now we know the value of A and B, we can construct the equation for Greg's investment.
Okay, so now we have created this formula. I can work out Greg's investment after any amount of time. So say, after 30 days, the formula will be 2 times 1.5 to the power of 30. So after 30 days, Greg's investment is approximately $383,000. Seems like Greg's got a pretty good deal.
A defining aspect of exponential functions is the constant doubling time. As shown, when Greg's initial deposit of 2 increases to 4, it takes approximately 2 days. Again, from when the 4 increases to 8, it takes another approximately 2 days. Likewise, a decreasing function would have a constant halving time. This is one of the major significant characteristics of exponentials.
Another characteristic of exponential functions is that they have an asymptote along the x-axis where y equals 0. So this means the value of the function can never equal 0. It will tend to infinity and get very small, but will never reach 0.
Right. Exponentials have very important implications when it comes to things such as population growth. An exponential function is used to predict population trends. These predictions can then be used for things such as city planning. For example, city planners will need the predictions to know where to build hospitals and how many to build. They'll be able to know if the population can be sustained depending on the resources that are available at the time. There are other industries in which exponentials are used to show many other trends of growth and decline.
On behalf of Group 22, we hope this video has been informative and has showcased the nature and properties of exponential functions and how they are relevant in nature and in the real world. Thank you.